Hello everyone, and welcome to another video on the compilation process. In this video we are going to look at code optimization. However, before we do that, let's have a quick look about what we have covered so far. So we have looked at lexical analysis and symbol table construction. We have looked at syntax analysis and semantic analysis, and we have looked at machine code generation. As I say, this video is going to be about code optimization. But before we do that, let's have a quick look at machine code generation, the previous stage, as a reminder. So machine code generation is about taking your syntax tree that you produced earlier and looking for patterns in the code. Patterns that can be easily replaced with chunks of binary. So for example, I've got the pattern of an add here, and I've also got a pattern of an add here. What I can do is, as a compiler, I can say, oh, I recognize this part and I recognize that part. I don't have to think about it, I just have to replace this boom, with some binary. Boom. So for example, the add function might actually be the binary of 0101, for example. And all I do is I'd say, right, this, it's not actually that, it's 0101. And this one would be 0101. And maybe the mov is 1110. And I just chunk all these binary parts into things I recognize. Eventually, what I would do is I would produce an assembly representation of this program. So this tree here becomes assembly language. So if you remember back to Little Man, and assembly language is able to run on CPUs because it is basically a one-to-one mapping with binary. And what we do is we translate this assembly into machine code that can actually run on the CPU. So just to recap, Python does not run on your CPU. The computer cannot read Python. It cannot read assembly language. It can run the assembly language by turning it into binary using an assembler. And at the end of machine code generation, we get all the binary that represents our very, very simple statement here. So in binary, this one line equates to 1, 2, 3, 4 lines of assembly, which equates to 4 lines of binary. As you can see, simple lines in Python translate to a lot of binary lines. Okay? So, how does machine code optimization come into this formula? Let's have a look at that. So, optimization. What's it all about? Well, why do we optimize to start with? What's the point of optimization and what benefits could there possibly be for it? Optimization is about speeding up your programs. It's about using less lines, less memory, and making it easier to understand. So, what things in a language are potentially slow, use a lot of lines, maybe a lot of memory, and are hard to understand? Well, there's a few things. One thing that we try to optimize in terms of programming are loops. And you might think, wait, aren't loops a good thing? And yes, they are. They are useful. They have a job. However, what this actually means is your program is darting about in lots of different places. So let's say this is RAM, or the CPU registers, and you've got lots of lines of code, and your loop starts at line 1, 2, 3, ... and let's say it ends at line 50 for the sake of argument. We've got line 51, 52, and so on. Your program will start at line 1 and it will work its way through. So let's say the loop starts here and it ends here. It says go back to 1. So it goes 1, 2, 3, all the way to 50, and then it goes back to 1. That's going to involve a jump back up to number 1. However, let's say your program was even smaller than that. Let's say it had 4 lines, for example. And we had loop, and we had on line 3 at 1. You'd think, oh, that's still okay. I'm going 1, 2, and then back up to 1. 1, 2, 3, back up to 1. And for the most part it is. It's okay, but it's not efficient. What do I mean by that? Well, normally if you execute a program one line after the other, you just move down a line, and that's easy for the computer to do. All it does is it increments the program counter by 1 to move on to the next line, and that's a very simple thing for the CPU to do. However, if you've got lots of different lines of code, in the thousands, perhaps, thousands of lines of code, and you're looping between them all or jumping around, what that means is the program has to go back to a line that it previously went to, which takes an instruction to do. So if you're looping a lot, such as this one, it means every other line, so we do 1, 2, 3, and then we perform a loop instruction. So let's do a little loop here as an instruction. It's taking 4 lines to execute this loop rather than just the 3 that you see, because jumping is still an instruction that the compiler and CPU has to do before it can execute this code again. Likewise, this doesn't take 50 lines, it would actually take about 51, because one of the instructions has to get you to loop back to the top. So using lots of loops, especially nested loops, that means having a loop inside another loop, can make your program slower. How could we potentially get around this? Well, one thing we can do is we can use linear code. Now let's say my loop was to say x equals x plus 1. And let's say we were doing that 10 times. What I could do is, rather than jumping backwards and forwards, I could analyze this loop in this code, and I could say, right, instead of doing loop x equals x plus 1 for 10 times and then going back, what I could just do is say x equals x plus 1, x equals x plus 1, x equals x plus 1, and so on, 10 times. How will that have a benefit? Well, on the one line for the 4, it says, right, we're going to execute the 4. The next line down is executing the actual statement, x equals x plus 1, and then we jump back up to 1. But we're doing that 10 times. So rather than executing this code 10 times, so x equals x plus 1, because we want to do it 10 times, remember, what I'm doing is I'm actually using 20 instruction cycles, 20 clock cycles in my CPU to execute this instruction. And you think, well, why is that the case? Well, I've got x equals x plus 1 on my first iteration. I then do a jump. I then do x equals x plus 1, and then I do a jump. I then do x equals x plus 1, and then a jump. And already I've used 6 lines of code here. Whereas, when I do an inline function or loop, what happens is the program thinks intelligently. It says to itself, okay, I can just pull that out and copy it 10 times. And what happens is, when we do it 10 times, I just do x equals x plus 1, move to the next line, x equals x plus 1, move to the next line, and so on. And what happens is, when I do an inline execution, or a linear execution, something that goes in order, it means I execute 10 lines. This one uses 20, all because we're jumping every time we want to execute this statement. And in fact, it gets even simpler than that. Let's say instead of doing x equals x plus 1 10 times, how many times do I want to add 1? Well, I want to add it 10 times. So we could save 10 lines just by saying x equals x plus 10. That's another big efficiency gain right there, because instead of 20 lines or 10, we've just used the one line. And that's where looping comes in, an efficiency, with optimizing your machine code. So what we've done is we've gone from a big whacking loop to maybe a little one, to a single line of code that has been intelligently thought about, either by yourself or by the compiler. And this is one way that you yourself can actually speed up how your program executes. Otherwise, doing a loop uses more instruction cycles and takes longer to execute your program. For very short programs, this won't make much of a difference, but if you've got a big long program and it's very memory intensive, then it can slow down your computer a lot. The next way that we can optimize our code is looking at if statements. If statements, and you're thinking, oh, why do if statements need optimizing? They look okay to me. They're no problem. The problem is the computer cannot predict what's going to happen next. What do I mean by that? Well, let's say I've got my RAM or my registers in the CPU, and I've got the instructions X, Y, Z, A, B, C. Doesn't matter what these instructions are, but I'm following them in this order. If I'm following these instructions in this order, I can load them all into the CPU at once. I can say, right, you're going straight to cache. All of you are going straight to cache. I don't have to care about anything else. And the computer moves on to another set of instructions, or another group of instructions. And what we'll do, the CPU, is it'll just go through each of these instructions one by one, and life is good. And it saves a lot of time and energy, because it doesn't have to load them in one at a time. It just takes them all, dumps them, and goes on its merry way. This was where an if statement becomes a bit of a problem, because the computer has to reset the fetch, decode, execute cycle every time you execute an if statement. Why is this the case? Well, it's because, let's say for example, I've got an if statement, if x is greater than 10, as an example, and this has 1,000 lines in it, 1,000 lines. And let's say else x equals x plus 1, as an example of an if statement. Very contrived, but it's just an example. A computer would do x, y, z, a, b, c if it was all sent in a group. However, when we get to an if statement, the computer says, oof, I've got a choice now, and I don't know which one to take yet. I'm either going to load 1,000 lines into memory, or I'm going to load 1. If I load 1,000 lines into memory, and it turns out this is false, that means I'm actually going to execute this line here. And if I am executing this line and not these 1,000 lines, that means I have wasted a lot of CPU cycles loading all of these lines into memory. So it's saying to ourselves, why bother loading 1,000 lines into memory that we might not need, when I could wait and see the result of this and maybe just it load one line. So it's about looking at efficiency here. You can't predict what's going to happen in your program. The user might enter input that you don't expect, or you might have a lot of different outputs for your if statements. And you can't load all of these if statements into memory. Let's say this was actually an elif. And let's say I had another elif that said load 500 lines into memory, and then I had an else of executing 5 lines. All of a sudden, my situation has become even more complicated. Why? Because I've got an option to load 1,000 lines, I've got an option to load 1 line, I've got an option to load 500 lines into memory, or I've got an option to load 5 lines. And we sat there thinking, oh, well, that's what, 1,506 lines I would have to load into RAM, and then into cache and the registers. The computer cannot fit that many instructions in its CPU at once. It just cannot do it. And maybe the programs might be bigger. So what we have to do is we have to wait for the result of this if statement to find out which of these we do. Once we know which ones we're doing, we can load all of those lines into memory, or this one line, or these 500 lines, and so on. Once we take those blocks of lines and put them in memory, it'll execute just like this example here. It'll just go through them all, and then it'll leave the if statement. However, it then becomes even more complex if we have nested ifs. That means if we have an if inside of another if. Why? Because I could have an else that says, well, I've got 500 lines here, then an if, and then another 500 lines, and then I've got 2 lines here, for example. If I take this, well, I'm going to have to load 500 lines, and if this if executes, I'm going to have to add another 500 lines in there when I get to it. Alternatively, I might just end up loading 2 lines into memory. What this does is, it means every time you want to execute an if statement, it means it has to stop what it's doing, wait for the potential condition to become true or false, and then figure out what it's going to do, because it cannot preempt your code for you. Okay? And what this means is it slows down your programming. What can we do? Well, we can take that code, we can split it into chunks if we need to, or functions, and we can put them in different places that will execute at different times. Generally speaking, for if statements, it's not as easy as loops. All things said, jumps are a very cycle-consuming construct. Jumps, that's from the loops when we were jumping around. Each jump adds an extra line of code for your CPU to execute. And with if statements, it's a bottleneck problem. It means we can't predict what happens, so we have to take it one step at a time, which means it increases the length of our programs and the time it takes. So, code optimization is about reducing the options available and simplifying things. So, for example, we could potentially simplify these options here. We could say, well, we could take out part of the if statement. We might not need it at all, in fact, depending on how you've programmed it. Up here, we could just rewrite this loop that adds x equals x plus 1 10 times into a single line where x equals x plus 10. This is much easier to understand, this x equals x plus 10, than a loop. So it's more efficient. Okay? It uses less memory, it uses less lines, and it speeds up the program. That's just one type of optimization. There are so many more ways of optimizing our code. All you need to know for your GCSEs is that code optimization simplifies your code, it speeds up the program, it uses less memory, less lines, and it's easier for programmers and the compiler to understand. We make things more efficient. If you ever need to include an example, I would recommend using the example of loops, in that every time we loop, we need another instruction to return at the start, which for very short loops can lead to a lot more instructions executed unnecessarily. Okay, that's it for optimization for now. Thank you very much for watching. Remember, you do not need to know all of the information I've gone through in terms of compilation from these videos. All you need to know is the content from the first video in this series that summarizes compilation. Otherwise, these videos are intended to jog your memory at any point by connecting different bits of information that will then bring you to other parts of the compilation process. For example, if you remember about optimization, you'll say, well, okay, in order to optimize, we need to have the machine code. What do I need when I've got my machine code? Well, where did it come from? It came from a syntax tree. Oh yeah, syntax tree analysis exists. How did I get there? Well, oh yeah, lexical analysis. I remember what that's about now. So overall, I hope this is helpful, and I'll see you again at some other point. So thank you very much for watching.